I rephrased the topic of my talk as this question: how did mathematical models contribute to improve our understanding of HPAI and ASF transmission patterns, and to support management decisions for the ministry? So that will be the question that I will try to develop during the next 20, 25, 30 minutes. Okay, so first, just wanted to briefly recap what mathematical modeling is. So modeling in general is a simplification of reality, and mathematical modeling is a simplified representation of what we call a complex phenomenon, where the parameters that define this model are described by symbols and linked with formulas. And so in these mathematical models, we can distinguish the statistical models and the mechanistic models, and this is the latter that I will talk about mostly today, the mechanistic models. But if we look at if we type mathematical models modeling infectious diseases in PubMed, we can see that there was a huge increase in the number of publications over the last 30 or so years, with a start of a noticeable increase in the late 80s. So that's the red line here, with the last point being 2024. And the green line is the same if we also add in the PubMed query livestock, cattle, pig, poultry, so animals. And so we can see that we are far behind what has been done in human health. But if we zoom in, if we change the scale here, we can see that the trend is exactly the same. Okay, so there was since the 90s, there was an increased interest in the use of models to explain infectious disease patterns. And so, as I said, I will focus in this presentation in the mathematical models, and in the mechanistic models. And the mechanistic models are a type of mathematical models where the relationship, where we try to explain the mechanisms that are thought to have given rise to the data. And the most famous mechanistic model that we all heard about is the SIR model, compartmental SIR model. And this is the type of model I will talk about today. So if I had to distinguish the two main objectives of mechanistic models, I would classify. I would use this classification. So the first objective to me for mechanistic models is to try to understand and quantify infectious disease transmission processes using past epidemics. Okay, so epidemic that happened, we try to characterize them, we try to develop a model to fit the model to the data to try to explain what happened, understand and quantify infectious disease transmission processes. And then there is the other objective, which is to predict the development of infectious disease epidemics. So in that situation, it's mostly based on simulations, and we try to see what could happen in the future or what could happen under different scenarios of management, for example. So let's just take the first objective. So the general approach for this first objective is that we usually have some epidemic metrics. Okay, so in this situation, in this graph, it's the incidence per day. We have the number of new cases occurring per day, but it could also be, I don't know, the result of a seroprevalence or several time points where we calculate the proportion of infected animals. Or so we need a measure of the epidemic. Then once we have a measure of the epidemic, we define the model that we think have given rise to the data. So in that case, we can I don't know. Let's assume it's something like foot and mouth disease. We can assume that the disease transmitted within the flock according to a SIR model, and this model is defined by some parameters, but we don't know the value of these parameters. So what we do is that we try to fit the model to the observed data to be able to reconstruct the epidemic. And like this, we have a model that is fit to the data that can reproduce the observed data. That's the main approach for this first objective. And the purposes of this first approach, can be classified in different ways, but to make it simple, is first to estimate transmission parameters. So using this approach, we can estimate basic reproduction number. We can estimate, I don't know, the duration of an infectious period or the duration of a latent period, for example. Then we can also estimate the relative importance of different hosts, especially when we have a multi-host transmission system. So what if the host A, species A, plays a bigger role than the species B? We can quantify this using these mechanistic models. And we can also estimate the relative importance of different transmission routes. Okay, if we have a pathogen that can spread through different routes, then using these mechanistic models, we can quantify the relative contribution of these different transmission routes. That was for the first objective. The second objective, is to predict the development of infectious disease epidemics. So to predict something that is not being seen at the moment. So the general approach for this is that usually we have a model that is already calibrated. So we have a model and we have values. We have assigned values to the parameters. And this model has been calibrated either using the literature. So we know there have been some transmission experiments somewhere. And so we extract the parameters from these transmission experiments. We apply them to our model, for example. Or the other way to calibrate this model would be to use the early phase of an epidemic to fit the model to the early phase of the epidemic. And that would help to assign values to the parameters that define the model. So once we have a calibrated model, we can simulate the model. Okay, we can make run the simulations, and that will give us the evolution over time of the number of susceptible, infectious, and recovered individuals. If we want to go further, then we can use this model to define what-if scenarios, and these what-if scenarios can be defined based on the surveillance strategies or on different prevention strategies or interventions that can be applied. Some can be hypothetical, some can be already implemented. And then under each of these what-if scenarios, we can simulate the model and look at the trajectory of the epidemic. And from this, we can synthesize these different trajectories and compare the different scenarios in terms of different epidemic metrics, like I don't know, duration of the epidemic or number of infected farms, and so on and so forth. So that's the general approach of the second objective. And the purposes for this is first simply to predict the size of an epidemic. If we are at the very early stage of the epidemic and we manage to estimate the parameters based on the very early stage of the epidemic, then we can project what would happen in the future and predict the size of an epidemic. So that is exactly what has been done for the COVID-19, for example. At the very early stages, there was some estimation of the R0, and then we could estimate the number of people who would become infected in the end, assuming management strategies would remain the same. And then the second purpose is to assess the effectiveness of management strategies. So that's exactly the what-if scenarios. You can say, okay, we have a strategy A, B, and C. We define them in the model, we run the model, and we compare the different strategies and say, okay, this one is probably more effective because it reduces the epidemic size, etc. So now I have set up the scene for this modeling purposes. I would like to illustrate some of these objectives using some work that we've done either in the lab or in other labs with application on highly pathogenic avian influenza and African swine fever. So let's start with avian influenza. Okay, so just a quick overview. I'm not so familiar with the situation in East Asia, but we've been working mostly in the context of Europe. And so what has happened during the last almost 10 years now, that we saw a dramatic shift in the epidemiology and the circulation of avian influenza viruses in Europe. So this is a figure taken from an EFSA report that shows over time the number of reported outbreaks. So the number of farms infected in Europe since the emergence of the H5N8 subtype clade 2344b. So autumn 2016 mostly. And so we had like seasonal peaks every winter, except during the different epidemic seasons, almost between 2017 and 2019. But it started in 2016, 2017 with a dramatic epidemic in Europe with 1,200 outbreaks, and France accounted for almost 40% of them. So there were 484 outbreaks in France that year, which was never seen before. So that was a great shock, and that triggered a lot of research to work on avian influenza in France and Europe. And then there was nothing for almost 2 years, well, almost 3 years, because this was a very small epidemic, 300 outbreaks in the whole Europe. And then during the winter 2020-21, there were also a major epidemic in Europe, France accounting for 40% of the outbreaks. And then during the summer 2021, a new virus emerged, which was of the subtype H5N1, and this is the moment when everything started to change. So from this moment on, the virus was circulating in the wild birds all year long, posing a constant threat to the domestic poultry. That was a big change, because before it was really seasonal, and then it started to become a bit less seasonal. You can see here, for example, in May 2023, we had in France a surge of epidemics. So this is Europe, but we can see the surge in France in this graph, where there was in May, so a moment of the year when usually there is no HPAI, a surge with almost 100 outbreaks in one very specific location in France, where there were a lot of between farm transmission events. Well, anyway, and so that's the big picture of what happened in Europe, and that triggered a lot of work, and especially in our group. So we've been working on HPAI for quite a lot since that time. So one of the first things we did back in 2019 was to try to develop an application that could help policymakers or the administration, the vet services, to conduct the outbreak investigation. So our objective was to estimate the time of the first infection in a flock that became an outbreak. So in the end, what we did is that we took the registry of different farms that became an outbreak, and we looked at the daily mortality in these different farms. And so that's the column jour here, day. So that column reports the number of dead ducks every single day for the months of December 2016. And so you can see that it's very low, and then it increases from 17 to 20 to 106. And so we have this incidence every day for almost 60 farms, because we collaborated with people from the Netherlands who got the same data. And with this data, we used a mathematical model where the birds could go from the susceptible state to exposed, then infectious, and then once they were infectious, they could either die because of the disease, going to the D compartment, or they could recover here. And there were different parameters in this model. And so we fit this model to the observed incidence, daily mortality incidence, to estimate the transmission parameters, and most importantly, to estimate the time of the first infection. So this figure here represents the dotted black line represents the true observed mortality rate. So it's almost 0 all the time, and then it increases during the last two or 3 days. The blue envelopes here represent the predicted number of dead animals predicted by the model. So we can see that it's quite nice. It fits quite well. But the model also estimates T0, and T0 is the day when the first animal became infected. And so we can estimate it from -15 days to -5 days with 50% credible interval between -11 and -7 days before notification. We could also estimate the reproduction number within the flock around 17. And so that was one thing, and we could also reconstruct the evolution over time of the other states. So the blue one here is the evolution of the number of susceptible animals within the farms. And the red line here is the number of infectious individuals within the farm. And what we saw is that at the moment when there was the reporting, the suspicion, at day -1, then there were already more than 10,000 infectious birds in the flock, showing that it goes super, I mean, it spreads super fast within the flock. So when we have a suspicion, the flock is already super infectious. It's kind of a viral bomb for the other flocks around. So we applied this approach to many different flocks from the Netherlands and from France, from different epidemics from the 2016 to 2023. And these graphs represent the evolution, the different estimation of the time of the first infection in all these flocks. And so in the end, we developed a online application to provide support to those who have to make an outbreak investigation so that they can estimate the most likely time of the first infection and then focus their energy when doing the outbreak investigation on this period instead of spending a lot of time investigating periods that are not relevant. So this tool is freely available, and actually, so you just have to specify which species we're talking about, the size of the flock, the time of the suspicion, and then the number of dead animals reported every day in that flock. And then by clicking submit, then the model runs in the background, and then different graphs and the estimation of the date of the first infection are provided by the software. Okay, so that was one thing. That's a work that was done by Sébastien Lambert, a postdoc in our group. Then during the 2016-2017 epidemic, I repeated, it was the first big epidemic of HPAI in France. And so there was a lot of uncertainty about the role of the different species and the role of the different hosts. So what was done is that the epidemic of HPAI in France was modeled using a spatial model, a mechanistic model that tried to reproduce both the time series of the number of outbreaks reported, which is the figure on the top, and which also tried to reproduce the spatial pattern of the transmission, which are the red dots appearing on this figure. So the model managed to reproduce quite well the epidemic, and most importantly, it allowed to estimate the relative contribution of the different host species, and mostly the ducks versus the galliform farms. And so what was found was very interesting, is that the duck farms were much more infectious than chicken farms, meaning that if a susceptible farm was at the same distance from a chicken farm and from a duck farm, this susceptible farm was much more likely to become infected by the duck farm. And also it was found that the duck farms were much more susceptible as well than the chicken farms, around 5 times. Meaning that if a duck farm and a chicken farm were the same distance from an infectious farm, the duck farm was much more likely to become infected than the chicken farm. And that's when we started to realize that the ducks are playing a very special role in the epidemiology of the recent HPAI strain that circulate in Europe. So from this, we could reconstruct spatially the distribution of the basic reproduction number at the commune level, at the municipality level, confirming the 2 zones which are known to be at high risk because of the high density of duck farms. Now, if we look at the density of hosts in France, we can see that it's very clustered. Okay, so we have two main production zones. So we have the southwest here, which is very blue and purple, meaning that it's a very high density of duck farms and sometimes high density of chicken farms. So when it's blue, it means that the location has high density of chicken farms and high density of duck farms. When it's purple, it's high density of duck farms, but low density of chicken farms. And when it's like this cyan blue, it's high density of chicken farms and low density of duck farms. And so in France, we have like two main production poles, regions. So we have the southwest here with a lot of duck farms and also sometimes a lot of chicken farms. We have this region as well, which has a very high density of duck farms, and the Brittany here, which is a lot of density of chicken farms only. And so what we did is that because we have identified that the ducks are playing a major role, we defined, that was the work of Billy Bozil, who was a PhD student in our group a few years ago. We defined different scenarios where the density of duck farms was reduced in the communes, in the municipalities where the density was the highest. So here the scenario A shows the density of the duck farm in each municipality, and that's the real scenario. Okay, and then we created what if scenarios by removing farms from our database randomly in the municipalities with the highest density, and that gave us these other types of distributions. And then we ran simulations of the epidemic in these different what if scenarios and we compared the different epidemics by comparing the number of outbreaks occurring during the epidemics. And by doing this, we could show that by reducing the duck farm density in the 20% municipalities with the highest density, then we could have reduced the epidemic by a factor of 3, which was quite important, and this has subsequently been implemented in the legislation for managing the epidemic of 2022-2023, because there was a law that passed to prevent the restocking of the farms once the cycle was finished during the high risk period. So just to wrap up for avian influenza, so what mathematical models have shown, we use mathematical models for different things. So first, we unraveled the role of ducks versus chickens, showing that ducks played a special role in the epidemiology of avian influenza in France and in Europe in general, but France is the country with the highest number of ducks. That helped us to identify high-risk areas where the legislation is not exactly the same as in the other areas. So in these high-risk areas, the restrictions are more stringent when the risk increases. We used mathematical models to support veterinary services in their outbreak investigations by using mathematical models to estimate the time of the first infection in the flock. We use mathematical models to inform surveillance strategies in vaccinated flocks. And finally, we use mathematical models to find potential solutions to improve the resilience of the poultry sector by working on the decrease of the duck farm density in the poultry sector. The way forward, what we want to do now is we want to improve our preparedness as modelers to be able to provide real-time support to policymakers when they need it. When the epidemic starts, we need to be ready and we need to be able to provide policy support in a timely fashion. And then, as I said, we want to improve our vaccination strategy, and we will use mathematical models to test different strategies.